So hi everybody. As the gentleman just said, I'm the CEO of a consulting company in London called Deep Learning Partnership. And I'm going to talk to you today about something I don't really do on my day-to-day job. It doesn't pay my rent, but it affords me nice trips to exotic places. So who here has heard of artificial general intelligence? Yeah, so quite a few. And so what we label today as AI isn't really AI, it's matrix multiplication. So I'm going to talk to you today about how we might actually get to AGI, and it's more of a neuroscience-based approach. It's how the brain works, it's how biology does it. So it's okay, everything that we've heard the speakers talk about so far, which has been labeled AI, is really deep learning or artificial neural networks. And the early creators of that said this has nothing to do with how the brain works, right? It's just, it kind of works to classify cats and dogs, and that's about it. Okay, we do a lot more than that. So how do we get there? Is it even possible to build an artificial brain, basically, how biology does it? And I'm here to tell you, yes, it is. I'll just give it away. You can go now, but if you're interested, I'll walk you through how that might look and how that might be done. Okay, so here's a little book I wrote for O'Reilly. It's a booklet. There's my company website. There's my Twitter handle. You can follow me. I tweet a little bit about AGI and sometimes quantum computing, my other hobby or interest. So this is what we're going to outline just briefly. We're going to look at physical systems, how biology does intelligence, and where we are with the non-biological. I've kind of just explained that in a broad sense. But we'll look at some of the, we'll go through the slides. Deep learning recap, and then we'll look at how we might build AGI and some of the theories, and in particular one called active inference that I find particularly compelling to how the brain might work. Okay, so at that point it's sort of theoretical neuroscience, so I hope I don't lose you. I try to keep this kind of high level and not too much code or anything, although there is code and math for this stuff. And then we'll wrap it up by saying, is it possible? How long might it take? Okay, so why do we even want to build AGI? Why don't we just stop here with the cats and dogs and, TensorFlow? Well, if we do, like DeepMind says, if we can solve intelligence, and we can use it to solve everything else. I mean, we're quite good at stuff. We've got here today, we've had Einstein's theory of relativity, we've had, quantum physics, we've had classical physics, Newton, all the big names. Why do we need any help? Well, clearly, if we do manage to figure this out and build an artificially general intelligent system, then we can accelerate progress, which is probably, we can all agree, is a good thing, right? Although some people like Elon Musk say that, let's not build it because it will straight away kill us all, right? Well, we don't know, but I don't think it will. Okay, so yeah, so I'm the anti-Elon Musk. Okay, yeah, I'm the opposite. Okay, so I'm an optimist. He's a pessimist. So, but he's a good entrepreneur anyway. So, what about all of these things here? AlphaGo. This is DeepMind in London. I'm sure we all saw it on TV. AlphaGo beating the best Go player in the world. Was that AI? Was that AGI? AlphaStar. It's a new project to beat the world's best video game players. A little bit more general, one might argue, than just playing a board game. Deep Blue, IBM's Deep Blue in chess, a landmark, and IBM Watson. That's actually natural language processing, so that's quite clever. That's quite getting a little closer to AGI maybe, because it's having to understand language. But was it just doing it statistically? Was it just a massive computer hardware system that could, crunch numbers really well and just do everything statistically? Is it how we learn language and understand language? I would argue no. So actually, all of those are just narrow AI. They're just statistical, mathematical analysis of big data sets. Okay, so it's not really how the brain does anything. if it were, I mean, we do all of that in that little 3-pound thing sitting above our shoulders, right? We don't need huge data centers. So clearly biology is doing it in a slightly different way. Okay, so how is it doing it and how is it different? So, well, first of all, to build something, we have to understand what we're building. What is intelligence, general intelligence? Well, it's all these things, right? So, we don't just classify things, we do all of that. I won't read them out because I've only got 30 minutes, and sometimes, I give this talk, it's an hour. But there's basically 9 types of intelligence there, maybe even 10. And this guy at Harvard, Howard Gardner, just mapped it all out. See, existential thinking, language, we can do math using ANNs, but the rest of it is pretty much music, creating art, spatial navigation. That's all. We can do all of that in 3 pound. We don't need a huge data center, hardware cluster of GPUs. So what's different? What are we missing? Okay. Well, first of all, how far have we come? Like I said, the mathematical part, we're like 50%. We're pretty good. We're not bad. We're about halfway there. Linguistic, but it's only statistical analysis. Spatial navigation, self-driving cars, robots who can navigate through systems. I'd say we're about, there's something called SLAM. I'd say we're about 50% there. That's the algorithm. Simultaneous mapping and I forgot what the LAM stands for, but don't worry. We're about 50% there. You've probably seen simultaneous localization and mapping. You've probably seen the Atlas, robot that do flips and run around outside and do good stuff. Boston Dynamics. So that's why I'm giving it a generous 50%. We do a lot more than that. We can do gymnastics. We can run around. We learn stuff very quickly. We don't need millions of data sets to train. But as we go through that list of 9 types of intelligence, it just gets worse, right? Robots understanding each other, or even algorithms running on a computer, virtual sort of intelligence. Intrapersonal, understanding themselves, and existential. Show me an algorithm or a robot that kind of questions why it's there, or even understands that it exists. It's kind of zero, okay? So we haven't figured that intelligence out at all. So the brain is pretty special, right? Biology is kind of special. We could argue, are chimpanzees self-aware? Well, yes, right? Are dogs, cats? Probably. And as you go, snails, maybe not. Bacteria, no. So there's clearly a continuum in what makes us a little different is our neocortex, that sort of outer layer of the brain. So we kind of have to figure out how that works, basically. But we've got all this other stuff in the brain, like the amygdala for emotional intelligence, the reptilian brain, and there's sort of layers. You can trace it. In fact, as babies are born and embryos develop over the 9 months, human baby, you can see, evolution. It starts off, with the, reptilian brain and goes out, monkey, and then, humans, as we develop in the womb. So it's all of that evolution is still captured. All that information is actually captured by biology. It's just that last layer, the neocortex, that makes us be able to come up with, science, special theory, relativity, whatever, so what are we missing? Why can't we do that yet in TensorFlow? Okay, why can't Google or DeepMind do that yet? So how will we get there? Well, it takes a village to create a child, and I'm going to argue it's going to take a big community to create AGI. We're going to need computer scientists, physicists to understand the physics of the brain, neuroscientists, clearly, and also psychologists. So what I'm seeing really at the moment, where these teams trying to build AGI or AI, just computer scientists, they're clever people, they have PhDs in computer science, which involves a lot of math and understanding hardware and algorithmic complexity. But it's not really understanding much about biology at all. Okay, so we're going to need a whole bunch of people. And so I'll speed up a little bit now. I've kind of laid the foundations for what we might need. So this is basically what we've got in hardware. So this is how biology does it in hardware. So, like I mentioned, we have a continuum from bacteria That's the simplest. C. elegans is the simplest biological system with a central nervous system. It has, I think, about 300 neurons. Then the bumblebee, the humble bumblebee, with about a few million neurons. And then us with about 80 billion or 100 billion neurons. Okay. So that's basically, maybe if we start at the simple, the C. elegans, and then build a bumblebee, then maybe one day, we'll get to us. That's one sort of thought. The other observation really is that nature is very hierarchical. We're built, neurons are built of, they're not magic, they're built of atoms, molecules. And then if we just go up the different layers, we have synapses, neurons, then collection of neurons, this connectome. So these 80 billion neurons are organized into some kind of structure. Maybe, we should start there. So the question here is, what level do we start at? Do we have to start at molecules, or can we start at neurons, or should we start a little more holistically at the connectome? And on up until the central nervous system, us, which is about a meter in dimension. So we're going from 10 to the minus 10 up to a meter. So it's a hard problem. It's kind of no wonder we haven't solved it yet. There's a lot of physics in there. And so that's what it looks like. This is how nature has done it. It's complicated, isn't it? Do we need all that little tiny microstructure? Probably not, I might argue. This is how, what are we, 4.5 billion years of evolution on the Earth, maybe 1 billion since the first sort of organisms, bacteria, whatever, the first, primitive life. So over that billion years, this is what nature's ended up with, right? This is what makes us intelligent. These things, right? You couldn't guess that. You start with a blank piece of paper, but this is just the universe we live in, the laws of physics. This is how we work, okay? So there's no magic, but there's certainly a lot of complication. It's this complicated looking thing. That's a neuron, okay? And so the next level of the hierarchy, we see that these neurons are kind of organized into some kind of structure called cortical columns, which each have about 2 million neurons. So maybe this is a good level to start. Maybe we don't have to go right down to all that complicated structure, maybe here. So that's kind of an interesting thing that we know. And then up onto the connectome, and then the central nervous system. If we want to build a robot that does flips, we'll probably need all of that connected to the brain at the top. Okay, so, and then we have societies where we're organized into societies. Bees are, in their swarms, and humans in their villages, towns, cities, countries, and then the global national community. So there's all these layers of hierarchy, which are intelligent, right? So, we have this kind of macro meta-intelligence built into communities and systems of communities, which has enabled us to, survive, reproduce into the next generation. So, okay, so that's biology, that's how it works, that's how it does it, that's what we know, plus a whole lot of other details, which I haven't really covered. So what have we done, how far are we along the line with hardware? So basically, the talks that we'll see here, talking about CPUs, HO, GPUs, that's what they use, sparkling water all runs on these things. There's a new sort of endeavor to build ASICs, which are specialized for deep learning. But again, it's just narrow AI, it's matrix multiplication. But is it Grok and Cerebras, GraphCore, Intel Nirvana? They're all coming out with these amazing things that can do, petaflops operations, which is more than the brain does. It's actually more than biology does. But all they're doing is multiplying matrices, right? They're incredible feats of microengineering, incredible. These fabs cost, billions of dollars to build. They've all raised, GraphCore just raised $200 million. And they're impressive things, right? And that's what they look like, that CPU, GPU. There's a Google TPU, which is an ASIC and runs in their data centers. You can hire them, run them in the cloud. And then there's the GraphCore IPU. And they all look the same, but the microarchitecture is a little different. So this is all digital, classical. This is what, if you do computer science, you'd understand, the details of how bits move around in there, how much energy it takes, how the memory and the processor interact together. But they're not intelligent, right? They're just very good mathematical processors. Okay, that's what 100 petaflops looks like. And you can, log in today to these things in the Google data center. This is the most powerful, 3 exaflops, for goodness sake. That's almost 1 million times more powerful than the brain, but it's as dumb as a brick. It's incredibly impressive engineering. It takes up a football field. It's a data center size, but it can't do much except for multiply numbers together. It's not intelligent. Okay, so clearly we're heading into a dead end if we just follow that computer science, classical digital hardware route. See, the brain does all of that and all the other types of intelligence in that little 3-pound mass. So clearly it's not just about speed of compute, right? It's not just about horsepower. So what is it about? Okay, so recently, some of you, who's heard of neuromorphic computing? Who's heard of that? Yeah, maybe a few, right? A couple. So there's a project called Spinnaker in the UK. There's there's IBM True North, Intel, Leohi. There's a few different projects that are trying to mimic how biology in hardware does computation. Okay, it's called neuromorphic computing, so it's based on the brain. And so there's Steve Ferber. He's one of the guys who founded the ARM processor company. And so he, 20 years ago, left ARM and started on this neuromorphic journey. He's based at the University of Manchester, and recently the Human Brain Project has folded, it's called Spinnaker, into itself because it's bioplausible hardware. So they have lots of nice funding now. Again, there's IBM True North and Intel. I mean, these companies have a lot of money too. So that's what it looks like. So there's 5 racks there. That is about as powerful as the brain of a mouse. So it's not human level yet, but it can do things. It can go through a maze. It can solve Sudoku and stuff like that, just like we do. So it's kind of getting there. And I would argue, to build intelligence, rather than just simulating it on classical digital hardware, this is a more intelligent route to take. Okay, so, and there's a little bit of detail. So this is an important, technology and a new path that not many have heard of here, which is very interesting. It's probably like we were in the 50s with digital computing. There's just a few mainframes in the world right now, a few of these devices, but they actually exist. And you can actually log into Spinnaker as part of the Human Brain Project. You can create an account and log in and watch it do stuff in real time. So they're not these magical, mystical things in a lab. They're kind of getting in real. And let's see. So that's okay. That's another one, initiative from Heidelberg, the Brain Scales Project, which is also part of the Human Brain Project. So the one on the left, I would argue, will get us to general intelligence. The one on the right, no matter how impressive that looks, won't. Okay, so, and then there's quantum computing. How about it? Is the brain quantum? No, it's warm, it's squidgy, nothing to do with quantum at all, okay? Although birds navigate and plants photosynthesize using quantum processors, but it's not really generally how we do it, okay? But the pictures look really nice. I decided to include a couple, and there's what a quantum circuit looks like. I also quite like quantum computing because I have a physics background. But it's probably, we don't need to worry about that if we're building AGI. It might help some of the computations initially, but ultimately we're not a quantum computer up here. It's a neuromorphic computer. Okay, so that's the sort of 4 different types of hardware, and I'd argue the one on the top right, neuromorphic, will get us there, and that's how they look in a little bit more detail. And so, it's not magic, it's just really hard engineering, which is why we haven't built it yet. It's just hard, okay? It's small, it's, and to understand it, it's difficult. Do we have a mathematical theory of the brain? Well, I would argue, sort of. Before I go there, so the data center of the future right now is just full of those very clever chips we saw, the graph core, the TPU, GPU, CPUs, very amazing engineering. But soon we'll see them being filled up with neuromorphic and quantum as well. So Google announced quantum supremacy last week, a couple of weeks ago, which means that a quantum computer, it can do something faster than the biggest classical computer. So the data center of the future will look like this. Okay, so we're entering a very interesting time in human history, I think, in terms of computation, because we haven't just got classical computing, we have neuromorphic and quantum as well coming online. It's been 80 years, right, since we first started doing the computation. So we're at a very interesting time, I think, in the history of computation with these other two major types of computation coming online. So deep learning, I've argued, that won't get us anywhere near intelligence. It will classify stuff really well and do a little bit of statistical language processing, but it doesn't do the 9 types of intelligence, okay? And so the most popular framework by far is TensorFlow. PyTorch is kind of also increasing in the last little while. But, you know, general intelligence, how biology does it, it doesn't do matrix multiplication. So deep learning is not AGI. So we won't talk about that, but we will talk about more neuroscience stuff, okay? Sorry to be so harsh, but you know, it's reality. All that clever stuff isn't actually AGI, but it's good at certain things. Okay, so so what do we do? I mean, where do we even start, right? With the general theory of intelligence. Well, you know, the brain is a physical system, right? It's just 3 pounds of physics, just. Okay, so what do we know about physics? Well, we've pretty much discovered all of the laws of physics, I think. Dark matter's kind of a new one. It's a bit of a bold statement. I'm a physicist, so I'm allowed to say that. So what out of there do we use, okay? You know, probably thermodynamics and electromagnetism in a complex system, right? So it's nothing magic. Now, the underlying theory of all of that can be described in something called the principle of least action, which is that, and there's just been a book published last year. Surprisingly, it wasn't one before, that sort of says, okay, all of physics, that's, you know, classical, quantum, everything can be, you know, derived starting with this principle of least action. Now, if who's got a PhD in physics here? Yeah, a few people. And so this is what you get at grad school in physics, right? We do Lagrangians and Hamiltonians and principles of least action. So everything we learn F equals ma in undergrad, we're told, yeah, that's very nice and quaint, but really this is the powerful machinery that's been developed. But we don't, you know, that we get there, but I think we're not really taught that, you know, it's a very unifying principle. Okay, so I'm saying, okay, well, probably that's a nice place to start if we want to try to come up with a general theory of intelligence. Okay, it's a big statement, a bold statement, but you know, the brain's not doing anything that physical systems can't do. Even though it feels it is different, right? Because we have consciousness and, you know, that subjective experience and self-awareness and that kind of stuff. But I'm going to argue it's all just physics. There are people in the room and elsewhere who will say, no, there's something beyond physics, metaphysics. I'm not one of those people. Okay, so I'm just going to keep it really simple. So, you know, what can we do? Well, we can explain and understand what we see. We can imagine things, you know, imagination, imagine that. Problem solving, planning actions to make these things real. We can do all of that. That's what intelligence is, really. And we can build new models as we learn about the world. So probably, okay, we've got 5 minutes. So these are the sort of major, some of the major theories of general intelligence, mathematical theory. These are all smart people who have spent their whole lives dedicating to this. You can look them up later. There's a guy called Carl Friston at UCL in London, and so his theory of active inference is the one that I think is particularly compelling. And I won't spend any time going through the details because it's pretty hard math, actually, but he uses something called the free energy principle. It's based on physics and information theory. It's nothing kind of new and crazy. It's just applying it to the brain. And he is a theoretical neuroscientist. And so here he is. And we don't have time to play it, but so the slides will be made available, I think, so you can listen to him, and he's on YouTube if you want to Google it. And so that's how he sets it up. There's there's us agents acting in an environment. That's the same if we're bacteria, monkeys, birds, human beings. It's a system, right? A physical system. We act in our environment. The environment acts back on us. So there it is, bacteria to brains. And the math gets really ugly because it is statistical, probabilistic, and physical all at the same time. It's complex information theory, essentially. But the ultimate question is, can we build general intelligence? So I would argue yes, because we have theories. We have very compelling theories. All of those are, you know, hundreds and hundreds and hundreds, literally thousands of papers written, deep mathematical theory with keeps hundreds of graduate students in PhDs. So yes, we have the theory. We have candidate theories. We have the algorithms and software. We have the hardware, Neuromorphic in particular, and we have data sets nowadays. So yes, and I think we're kind of on our way with these projects like Spinnaker and IBM True North. So we're starting to build the hardware. It's just a sort of, it's always just an engineering problem, right? Yeah. So, you know, what else? So should we? That's an ethics question. We won't go into that because we could spend the rest of our lives arguing, should we do it or not? We're going to do it anyway. But, so there are some projects. DeepMind is trying to, although, you know, all the Go and stuff isn't general, it's just specific. But there's a whole bunch of AGI projects, and they're all super interesting. So I definitely encourage you to look and explore if you're interested in this subject at all on the internet. And in conclusion, so it's obvious that deep learning is just statistical. It's not based on physics at all. There's like zero physics in there, so it's definitely not going to get us anywhere towards general intelligence. But research groups many are looking into bioplausible models. That's both on the theoretical and the hardware side. We're sort of getting a glimpse of the very first systems. We have the rat brain there with Spinnaker, so we're sort of at the very beginning of a steep exponential. So maybe that will improve, and in 10 years we'll have a human-level brain which will be conscious and self-aware and subjective experience, which is kind of spooky and creepy, right? But you know, there's nothing. I'm trying to argue there's nothing that mysterious about the brain. It's just a complex system, and so. What do we do then? Well, you know, we'll figure it out as we go along, as we have done everything. And so the future of AI, Jeff Hinton, he's the godfather of AI. He's in Canada, and I'll let him have the final word, except there's no volume. Okay, so he's just basically saying that the brain is super... everything he's done in his whole life he's just clearly admits he wasn't working on general intelligence, and to figure out how it works, we're going to have to look at neuroscience. That's pretty much his message, and it's pretty much my message. And so I hope you've enjoyed my talk. It's been a little bit different from everyone else's, but thanks.
Yeah, and we have questions, of course. Okay. One interesting question is, could AGI be achieved without emulating human brain, but building a completely different model?
No.
That was a short one. You kind of answered this one, but maybe you can elaborate a little bit more. When do you think AGI will arrive? And I can follow with another one. As you said, you're at 50% of achieving AGI. What are the main challenges you are facing to get to 100%? Yeah. What technology breakthroughs are needed?
Yeah, so it's basically a hardware engineering problem. So I did show the Spinnaker, and you know, there are other hardware projects around the world doing this, like IBM and Intel. And so that's the mouse brain right there. So basically, it's a scaling problem now. I mean, we started at one transistor at one point with classical computing, and then companies like Intel were formed, and AMD and NVIDIA, and the rest is history, right? It'll go on its own Moore's law. So right now we're at the kind of like 10 transistor stage that we were with classical. So we'll just see that scale. I'm going to say something really bold. It's just a scaling problem at this point in time. So watch this space. Yeah.
So what will you say? When?
10,
I mean, can
10,
you predict?
Well, it'll go mouse, and then it will go, you know, bumblebee, and then, well, no, bumblebee, then mouse, and then monkey, and then human. So we're on a curve. So human in 10 years, that's my prediction.
Isn't that too optimistic? I mean, in 1969, when people flew to moon, they thought that they will be living on the moon by now.
Okay, I'm an optimist.
Okay.
I'm saying 10, yeah. That's
Okay,
okay.
and
But
the
I appreciate that.
The last one, a comment about the Soul Machines Baby X project and the potential to get closer to general AI.
What's that? Say that again. Yeah.
I haven't heard about the Soul Machines Baby X project.
Oh, yeah, I have. Yeah.
Okay,
So,
well, certainly.
what was the question? The Baby X?
I mean, your comment about it and the potential to get closer to general AI.
Yeah, I didn't actually mention Baby X, but that's a nice project in New Zealand, and it's another AGI project. But basically, it's going to come back to neuroscience. You know, we saw the math, we saw some of the mathematics involved. It's going to be people working at that level from a theoretical point of view, and other people like Steve Ferber and the Human Brain Project, you know, brilliant engineers basically working on the hardware level, and these people talking to each other. And I know Carl Friston and Steve Ferber do talk to each other, and building this very complex system.
Okay, Peter, thank you.
Thank you. Yep.
I will present you with a certificate. We gotta film you with a certificate. No.